How about we do some partials and crosses? Didn't we do that already last class? Did we do the partials and cross product of the unit sphere? We did. Let's save ourselves a little bit of time. What do you get when what did we get when we did this? Anyone? I think we got sine V. Will you go look? Or was it sine U? Sorry, my paper. I switched my U and my V on my work.
A squared.
Yes, a squared, but our sphere is. If you look at, you're looking at the other example. The one before that was a unit sphere. So we got sine U. If you go through the work, okay. So we're saving. Do you understand how much time we just saved ourselves? Right? Okay. All right. So now we go and plug in to our scalar function the surface. So our scalar function is x times y times z, which means I'm going to take the x component of my surface times the y component of my surface times the z component of my surface. Then multiply that times this dA. So I have cosine v sine u, sine v sine u, cosine u, that's x, y, z, then sine u, then dA. And we can combine things together, right? Do I have any questions? Double integral. Let's see. Let's get all our u stuff together. Looks like I've got a sine cubed u, right? And a cosine u. That takes care of this, 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 and this. And then I have sine v, cosine v, or cosine v, sine v. It doesn't matter how I do that, right? dA. You know, let's not do dA. Let's actually go to our limits. So we're going to have dv, du, or du, dv. It's your choice. It doesn't matter because they're constants, right? Trapped between constants. So I'll do the v on the outer one, 0 to pi, 0 to pi over 4 here. And in that case, I've got to go du, then dv, right? And now at this point, I mean, we kind of know what we have to do, right? I'm also going to notice here that all my stuff with u's in it can be separated from all my stuff with v's, right? And when that happens, we can split this into two integrals and multiply those two answers together. So I'm just going to do it just to show off that we know what we're doing, right? We're going to be like, okay, I know this is just 0 to 2 pi. Let's see. That's my v's, right? So let me get all my v's in one integral. Sine v, cosine v, dv, times, not plus, right? Integral 0 to pi over 4, and then all my u's. Sine cubed u, cosine u, du. Those should be pretty clean antiderivatives. Do you agree with that? This is a basic sub. Let u be sine v. Well, we shouldn't use u, but you let that be your substitution. The derivative of it's right there. So you should get, as an antiderivative here, 1/2 sine squared v. You're evaluating that 0 to 2 pi. Times, I already know my answer is 0. Right? What's sine of 2 pi? 0. 0, sine of 0, 0. This is all going to be 0, isn't it? It's going to 0 this out. But this one here, just again, we can just show that we know what we're doing. This is 1/4 sine to the 4th u, evaluated 0 to pi over 4. This one would not have given you a 0, right? You plug in pi over 4, figure it out. But since that first one zeroes out, I'm done. The answer is 0. Okay, so what does this answer represent? It is not the surface area of this surface. It's the surface integral. So here's the only way I can imagine. Here's the only real way I can kind of get you to think of this. Imagine on that little cap that at each point on that cap it had a temperature. And the temperature was exactly the x-coordinate times the y-coordinate times the z-coordinate. Let's just say that's what it was. Then this integral represents like your net temperature. And the net temperature here would be 0. So there's some positive and some negative, and it's kind of wiping each other out, and you just get a net of 0. That make sense?
But only on the surface.
Only on that cap. Only on that little piece. And it could be, you could have anything up there. No, you couldn't do mass. That wouldn't work because you'd have to have negative densities up there. Magnetic field, well, we don't want, fields are different. That's the next part of this section, is what if we're on that cap inside a vector field? Then you have basically like some sort of what we call flux. All right, we have like a flow through this surface. And we're measuring that, and that's what the flux is. So that's the difference between having a field versus having a scalar function. A scalar function is more like temperature. Temperature at each, a value at each point, right? Temperature is this at that point. Temperature is this at that point. A field would be, at this point, we have a vector in some direction with some length. And at this point, a vector in some direction with some length. That's the difference. Got it?
Got it.
Okay. All right, let's see what the next one is. All right, a couple of applications of this. By the way, I believe that's the only example I'm going to give of a surface integral. In the homework, I do a bunch of other ones, but that just gets you kind of going, all right? Oh, wait, no, I think I do one more. Someone can look at notes. I think I do one more, because we've got some special cases we have to look at. But here's some formulas. I'm not going to give you an example of these. I think you've noticed, hopefully you've noticed, that in one of the exams I gave you, you had to calculate center of mass in moments of inertia for a problem a couple of mini exams ago. It was real tedious. Then the last mini exam, I asked you to find the mass in the center of mass of a wire, which I never gave you a formula for. But the formula does exist in the book. For this, I'm going to give you the formula, all right? That's a big hint, that if you're having trouble with that wire mass problem, it's because the formula, you have to actually read the book a little bit, all right? So what if we have a sheet, all right, a surface, not a sheet, but a surface, and we want to know its mass in center of mass? Then if we know its density function, so we know the density of the material at each point, then we can do a mass by doing the surface integral, right? So that's exactly like the F was, right? I'm looking at the density at each point, and I'm adding them all up, and I get my mass. And then to get x bar, we do this. To get y bar, we get this. And then to get z bar, we do this. So this is all just extending off of things we've done. And so really, what we have in summary for calculus, right? I always want to erase that. It's not ever going to come off. We can find the density of a flat region, a lamina is what we called it, even if the density of that lamina is non-uniform. And to do that, we use double integrals. We can find the center of mass of three-dimensional objects, right, using triple integrals. We can find the center of mass of a wire, assuming that wire, we're assuming that the wire doesn't really have width to it, which is kind of weird, and we could argue about that. We can find the center of mass of that. And now we're saying if you have a three-dimensional surface, you can find the center of mass. And again, we could argue about that. How can you have a surface that doesn't have thickness to it? If it has thickness, then isn't it a solid? Isn't it? Three-dimensional solid? All right. But we can we can kind of get away with that if it's thin enough, I guess. All right, next. All right, we have a special case when we're doing surface integrals. In fact, there's 3 special cases. I'm only showing one here in the notes, but I'll write down the other special cases. And here's what it's saying. Let's say that your surface is actually easy to write. In other words, you can write it as a function of 2 variables. When we first started chapter 11, I believe, we were looking at functions of several variables. And we said if you have a function f of x, y equals z, then that draws a surface, right? And the domain was the ground. If our surface can be drawn like that, then the formula we have for surface integrals becomes a lot easier to do. Now, the sphere we just did could not be done using this special case because you cannot write the equation of a sphere as a function of just 2 variables. You have to draw it with the vector function. So we couldn't. Understand? So one example of something we could use for this is, let's say we wanted to do just like part of that cone. Remember that cone? What if I just wanted to do like part of it? I could use this as the surface, right? And not ever have to come up with r of uv at all. Okay? If that's the case, then this is what the formula turns out to be. Our x, which used to be the u, is just going to be itself. The y will just stay y, and the z will be the function of x and y. So what we'll do is, remember how in the previous problem we took the scalar function and we plugged in the vector function into it? Right? This time we're going to take the scalar function and replace x with x, replace y with y, and replace the z with the actual function of the 2 variables, which would have been like that cone, just the square root of x squared plus y squared. But then the magnitude of the cross product, this, if you do the computation of this, will always turn out to be this. Okay, so let's just look at what this is. Magnitude square root, right? 1 plus partial of this function with respect to x, partial of this function with respect to y, square them both. And what this shortcut allows you to do is not have to compute the magnitude of the cross product of the derivatives, because it will always turn out to be this. Always.
We had one just like this in 13.6, right?
Where
Where we did it was the same exact thing.
yes, if you're trying to find the surface area,
Right.
yes, there's a simple formula if it can be written that way. Okay. Now, you can extend this idea where if you have the same situation happening, but this time, let's say x is some function of this time y and z. And I should point out, the reason why we use g here is because f is already being used as this scalar function f. That's why we're not writing this as f of xy. We don't want f to represent 2 different things in our problem. So we use g here. So what if instead of being able to write z as a function of x and y, we can write x as a function of y and z? How do you think this changes? This will be f of what? G of yz, y, z, square root, 1 plus. I'm just going to write, I'll do it in order. That's the same notation, isn't it? Partial g with respect to y plus partial g with respect to z squared dA. See how it changes? And then the last one, I won't write the formula down. I'll just say what it is. What if y is some function of x and z? We'll have what? F of x g of xz, z, square root, and then this partial becomes partial with respect to x, and that one becomes partial, well, it stays partial with respect to z. Understand? I'll give you two examples of those two cases. If you write x is equal to square root of y squared plus z squared, or you write y is equal to square root of x squared plus z squared, and let me put the first one up here. Z is equal to square root of x squared plus y squared. The difference between all those is just the direction in which the cone opens, right? This cone goes up like this. This cone comes out the x-axis at us, right? This one comes, what, out the y-axis like this? Right. X, like that. There's my x-axis. I think you understand. Y'all see that? Okay. So if we have this scenario, we can use that formula, or this scenario, that formula, so on and so forth. I believe the next example I have here is going to allow us to practice with this. Can you all believe we only have two more class periods? Find the surface integral over the surface S of x with respect to the surface area, where S is the surface shown below. Okay, this is tied into why I gave you that handout and why we took some time on it, right? That's really big. Okay. I want to find the surface area, the surface integral over the entire surface, which means that we're going to need to do it one surface at a time. And you can look at this as, we're adding up the temperature along the outside of this object if it makes it easier for you to understand. So we want to find the total temperature on this side, total temperature on the outside, and total temperature on the back side, right? So what would you like to start with? There's three surfaces, right? We have, let's call this one S1, let's call this one S2, and let's call this one S3. That okay with you? All right. So what about S? Oh, you want to start with S2? Okay. What about S2? It's in the YZ plane. Can you tell what its radius is? It's a circle, right? It's 1, and you know that because this right here, the green one, look at the equation of it right here, right? The radius is 1. So you know this has a radius of 1. The equation of that is x is 0, right? And now we have to really think about what we want to do. We can do this easy or we can do this hard. Here's the hard way. The hard way, and I won't work through the whole thing, the hard way would be to come up with my R of uv, which draws that, which we practiced, and we should all know how to do this. You want to help me? 0. V cosine u, V sine u, u's between 0, 2 pi, v's between 0 and 1. This will draw me circles with a changing radius. The radius is going to change from 0 to 1, so it should draw me that entire disk, right? Once I've got this, I can go to my formula. I could find the partials of this. Let's call this sub 2. I could find the partials of this. I could cross them, find the magnitude. I could do all that, right? And just plug things into the formula and go. But maybe this is a special case. Maybe it's a special case. Is that back part, that circle on the back side of this, is it is it z equals a function of x and y? So is it like a surface like this? Like, is it a surface up here like this? No, it's not a function of x and y.